We have covered in a previous lecture the extended Kalman filter, so now we'll see an example. And this deals with tracking with an angle-only sensor. This is a passive sensor that measures the angle of arrival of a signal. In this case, it can be acoustic or electro-optical. And the model for this problem is as follows. There is a platform on which the sensor is located, and it moves in a plane according to the discrete time equations stating that the position of the platform at time k is an average position plus a perturbation delta xp. This goes on for 21 sampling times from 0 to 20. Similarly, the y position is an average yp plus the perturbation. So these average platform position coordinates are known, but the vibrations or jitter, this perturbation, will be modeled as independent zero mean Gaussian white noise sequences with unity variance Rx and Ry. Now, the model for the unperturbed platform motion, and we'll see a picture in a moment, is assumed to be horizontal with constant velocity. In this case, x is linear with the time, x bar, and y bar is a constant. And the motion of the object of interest, the target, is on the x-axis and is described by the state vector x consisting of x1 and x2 position and velocity along the x-axis, which evolves with unity sampling interval according to this equation. Transition matrix is 1, 1, 0, 1. There's a white noise that perturbs the motion. Again, because the sampling interval is 1, that's the t, this would be a t squared over 2, and we have this as the deviation from the constant velocity motion. This is a white noise, a piecewise constant white noise acceleration model. There's an initial condition to this. The object starts at location 80 and moves with a positive velocity on the x-axis equal to 1, and we have a process noise variance that is 10 to the minus 2, so it's standard deviation 10 to the minus 1, and it's zero mean and white. Now, the sensor measurements are nonlinear, and this is why the problem is nonlinear. As indicated earlier, at least one of the equations between the state equation and the measurement equation has to be nonlinear. Then we have a nonlinear problem. So there's a function h that depends on the platform position in x and y coordinates, so that's xp, yp, depends on the position of the target plus the sensor noise. The noiseless measurement, h, the function h, is arctangent of y over the difference between the target x and the platform x. So this is the angle between the horizontal and the line of sight from the sensor. This is also known as the depression angle. And the sensor noise, WSK here, is zero mean white with variance of 3 degrees squared. So the standard deviation is 3 degrees. The sensor noise, again, is assumed independent of the sensor platform perturbations and the process noise. So we have the standard assumptions. And the estimation of the target's state is to be done using the measurements, the noisy measurements, and the knowledge of the unperturbed platform location. Typically, there is either inertial navigation system that knows where the platform is, or GPS, or a combination of both. Will deal with these in the last chapter, number 12. And in addition to this, we have noise. So the platform's location is imperfectly known, and we have imperfect measurements, and we have an imperfect motion model. So we have a very realistic scenario here where there are quite a few uncertainties. And here is the picture. The target moves over the 20 sampling intervals from time 0 to time 20, from 80 to 100 on the average, because that's not an exact motion, exactly constant velocity motion, but it's a noise perturbed motion with slight noise. The platform with a sensor comes from behind the target effectively and measures the depression angle, the angle below the horizontal of the line of sight between the platform and the target. So the initial measurement is Z of 0, and the last measurement will be Z of 20. And again, these are approximate positions because that's a noiseless version. So this is the average motion of the sensor platform and the target. The platform location perturbations will induce additional error in the measurements because we don't know where the platform is. So we have two sources of measurement errors, one the measurement noise, the other one the platform location errors. How do we evaluate the effect of these errors? We carry out, in the same spirit as the extended Kalman filter, an expansion of the nonlinear measurement function h about the average platform position. So the noiseless version that we have here, the h, would be expanded. So the noisy measurement z will be approximately equal to the h evaluated at the average platform. This would be really like the latest estimate of the platform's location. xp bar and yp bar then depends also on x1, the position of the target, plus the partial of the function h with respect to the platform position times delta xp, plus the partial of h with respect to the platform y position times delta yp, plus the sensor measurement noise. So we see there are two sources of errors, really. There can call them 2 or 3. Delta xp, delta yp is platform position, and ws is sensor, which are all lumped into an equivalent wk, the overall error in the measurements. And these partials obviously will have to be evaluated at our best known location for the platform, which will be xp bar, yp bar. And high order terms have been neglected here. So, what about this equivalent measurement noise WK? What is the statistical characterization? Based on our assumptions, WK will be zero mean, and we can calculate its variance, EWK squared, and denote it as R of k, using those expressions, and fairly simple evaluation of those partial derivatives yields us a term that has the Rx, the platform X location uncertainty variance, and the Ry, the platform Y position uncertainty variance, plus the sensor measurement noise variance. So these three factors now combine to give us the overall equivalent measurement noise variance. So this obviously requires those partials, and we have used the fact that these random variables delta xp, delta yp, and ws are mutually independent. One thing we can notice immediately, we have a time-varying variance depending on the relative location between the target and the platform. The variance of the equivalent or total measurement noise we have to work with is going to be time varying. And this variance in radians squared is plotted here, and you can see it's around 3 × 10⁻³ radians squared. So we have a certain increase from the initial point where the target is far from the sensor, in which case the sensor's platform location perturbations have a relatively small effect, and as the platform gets closer to the target, the platform's locations come more into the picture, have a bigger impact on the equivalent measurement noise variance. Now, the state X for the target will be estimated based on our measurement equation with the knowledge of only this average platform motion. First thing we have to take care of is to initialize the filter. One way of doing it is we can write the inverse transformation of the angle z to the position x1 as an x1 hat at time k. This would work at time 0 and time 1 to initialize it, is a function g that depends on the observation z on the xp bar and yp bar, and is given by this xp bar of k plus yp bar over tangent of the measured angle. So what this does is transforms the angle measurement into the location of the object. By differencing, now we would obtain two such consecutive measurements at k, 0 and 1. We can obtain an initial velocity estimate, so x1 hat at 1 minus x1 hat at 0. So these are the two position estimates obtained by effectively inverting the function h from z and obtaining x1, and we divide this by t equal 1, that's the sampling period, we would obtain an initial velocity estimate. Now it's interesting to see what is the impact of the actual numbers for the problem at hand on the accuracy of the velocity estimate obtained by this two-point differencing method. So what is the variance of this velocity estimate? P22, that's the component 2 of the vector, has a variance P22 at time 1, given everything up to time 1, that's the first two measurements, will be, because these two position estimates are independent, just P11 at 1 plus P11 at 0, so the sum of the variances, remember, even though this is difference, when it comes to errors, the variances will add up, divided by t squared, and which is because t is 1, given only by the numerator. So what we have now are these two position estimation variances based on inverting our nonlinear measurement equation. Now, we have a 3-degree, which is 50 milliradian standard deviation on the measurement. So the variance is about 50 milliradian, the whole thing squared. If we multiply this by the range squared, which is about 80, we obtain the initial variance on the position as 4 squared. In this situation, what we have is a very large variance for the velocity estimate obtained by two-point differencing. Therefore, if we know, because the velocity of the target has been given as 1, we cannot use that information, but we know if it is 1, for this problem there is a maximum, and we assume that the maximum for the velocity in magnitude is 2. In this case, what we are going to do, we'll use an initial velocity estimate of 0 and a standard deviation or variance, that's the same thing, equal to 1 in this case. And we take the off-diagonal term, the correlation between the initial velocity estimate and position will be taken as 0. So what we have now is, having observed that the variance obtained from the two-point differencing is very large, much larger than what we could assume reasonably as an a priori variance, that is around 1, which covers our initial velocity. What we have is a better initial estimate using this a priori information. Then what we're going to do, use the initial position estimate as x hat 1, 0, 0, and the variance 1 for the velocity and initial velocity estimate 0. Now, let's calculate the error in the initial position estimate with more accuracy. We had a back of the envelope calculation. The actual one will be calculated using the delta xp, delta yp, and the delta z, the error in the angle measurement, which is the ws at 0. So these are the three components contributing to the initial variance of the position. These are the partials of the function g, which is the inverse transformation from z to x1, and we can evaluate these, and we end up using the measurement. Again, these will be evaluated at the measurement because that's all we have at that point. So the x tilde 1, the initial error in the position estimate, will be delta xp plus delta yp over tan z, and the delta z, that's the sensor measurement noise, times yp bar over sine square z. Again, because these three components are mutually independent, you calculate the variance, you end up with three terms, the square of each of them. No cross terms, they are 0 due to uncorrelatedness, and this is the final expression. So it's an Rx plus an Ri over tan square z plus an Rs yp square over sine to the fourth of z. Now, when it comes to implementing the filter, we have to consider the following issue. The target motion is naturally modeled as linear in Cartesian coordinates. The measurements are obtained in polar coordinates. Most sensors will measure not in Cartesian. In this case, it's really a partial measurement from polar. We don't get the range, we get only an angle. And that's because it is a passive sensor. The nonlinear function h is the one that relates the state of the measurements. So here are the options for implementing the filter. You can continue using the inverse transformation h inverse of z and convert the measurement from angle to position, which would lead to a purely linear problem, and the Kalman filter can be used, which is the good news. The bad news is that this inverse transformation can lead to errors which are difficult to account for. Namely, when you take a nonlinear transformation, you could introduce bias in using it. You transform measurements which have a zero mean noise. With a nonlinear transformation, you end up in the new coordinate system with a noise which is not zero mean, and you don't even have a good variance for it. And for this particular problem, it's very hard to come up with a statistical characterization of the noise after the nonlinear transformation. There's a reference here which will be discussed later that discusses a conversion from full position measurements in polar coordinate to Cartesian. This is an incomplete position measurement, only angle. If you have a range and angle, we have some exact equations, it turns out, that allow us to evaluate what happens when you transform those measurements from polar to Cartesian. But when you have an incomplete position measurement, like angle only in this case, it's more difficult. So that's one option. The second option is leave the measurements in the original form and use a mixed coordinate filter. The state stays in Cartesian because that's the natural, and the reason the state is naturally modeled in Cartesian is a constant velocity is a very easy model in Cartesian. However, in polar coordinates, from the coordinates centered at the sensor, this becomes a very nonlinear model. So if you have the simplest possible motion, which is constant velocity or nearly constant velocity, it becomes very nonlinear in polar coordinates. So we keep motion in Cartesian, and the second option would keep the measurements in polar or angle only and use the nonlinear function that transforms or relates the state in Cartesian to the measurements in polar. The implementation we'll discuss is the mixed coordinate implementation. Measurement was the line of sight angle coordinate, and the target state was in Cartesian coordinates. So what this was is keep everything as is, because the transformation of the measurement into the more natural Cartesian is hard to characterize its errors, and the nonlinear function h relates the measurement to the state. So what we have now is some results. The position and velocity estimates compared to the two values, and we see here the two trajectory of the target starting at 80 plus a little bit of noise, so that's not exactly constant velocity, it's approximately constant velocity. And here are the estimates of the position based on the initial initialization we discussed and the subsequent measurements. Looks like the position is fairly well estimated. The velocity, it's a little bit strange because we assumed it to be 0. We start at 0. There's the initial estimate. Well, it is 1, but the filter doesn't know that. It looks like it's going backwards, but then eventually it picks up that it is moving forward. This is a fairly noisy measurement. A 3-degree angle error is a pretty large error, but on purpose it has been chosen like this in order to show the potential difficulties of a nonlinear estimation problem. The normalized estimation error squared should be chi-squared 2 degrees of freedom. So based on Monte Carlo runs, you divide by the number of Monte Carlo runs. The average should be around 2, but what we have is a single run here. So what we have is the upper limit is 6 or 5.99, the 95% one-sided probability region, and we see that for this particular single run it does stay within the bounds. And we have the normalized innovation square. This is chi-square with 1 degree of freedom, and again its limit is 3.8, and it is on the average should be 1. It stays within reasonable bounds. If we do 50 runs, now Monte Carlo runs, and we use a two-sided 95% region, the upper limit is 2.6. This is 100 degrees of freedom. Chi-square, you divide by 50, so on the average should be 2. We can see that it is not staying within the 95% region. By the end it gets there, so we do have a problem here that the estimator is not quite consistent. It's not very far from there, but it is not quite consistent because of the unavoidable nonlinearities. The innovations, interestingly, exhibit more or less the opposite thing. Early, they stay within the region. It's a 1 degree of freedom, chi-squared times 50 and divided by 50, so on the average is 1. It's between 0.7 and 1.4 roughly, and by the end things are outside. So we do have some problem with the nonlinearities in this situation. The other issue of interest is not just the normalized errors, but the absolute errors. So what we have is the root mean square errors, and we have again 50 Monte Carlo runs, and we have the position estimation RMS error starts with a fairly high value 25, eventually it goes down to a pretty reasonable number somewhere in the range of 1. And for the velocity, again, starts at 1 because we initialized it with an estimate of 0 when we know, that's knowledge under the table, that it was 1. So that was the initial RMS error, and eventually goes down to something like 0.2, 0.25. Okay, so the 50 run Monte Carlo averages show that the errors are quite a big fraction of the time outside the probability region, and what this indicates is that the filter calculated covariance is optimistic because the errors are too large, so the covariance is small compared to the errors, or the errors are too large compared to the calculated variances. And the normalized innovation shows large deviations towards the end. So we have a problem. This filter is really not consistent. So this illustrates that in the presence of nonlinearities with large noises, and this was on purpose, a 3-degree measurement noise that's large, we can run into such consistency problems. So the conclusion here is that a very thorough examination of a nonlinear filter is needed via Monte Carlo runs to find out if it is consistent. And the reason for the inconsistency is the fact that linearization does not work well with large errors, and it is the measurement noise that really causes the problems here. Even a second-order extended Kalman filter does not work well in this particular case. Now, if the measurements are more accurate, namely the standard deviation is 1 degree or less instead of the 3 degrees, this filter does become consistent. However, there are problems where you cannot help, like in the measurement with an acoustic sensor, a sonar, a vertical array might have such large errors. This is where this problem originated, actually, with an object, submarine, moving somewhere close to the bottom. And if you can get a better sensor, then it is going to work well. So in any case, it's important to remember nonlinear filters have to be tested thoroughly. Linear problems, the issues are much less severe. So the model for the extended Kalman filter, we're going to summarize now, consists of the following. There's an initial state, which is an estimate, an approximate conditional mean, because the problem is nonlinear, which is available with an associated covariance. We showed you can compute it with a 2-point difference. With one measurement gives you position, 2 consecutive measurements by differencing can give you velocity, but it might not be advisable to use that velocity estimate. You can replace it with an a priori estimate if that latter one has a substantially smaller variance. The second model is system dynamic equation, might be linear or nonlinear with additive zero mean white process noise with known covariance. The measurement equation, again in general, nonlinear with additive zero mean white measurement noise with known covariance. So at least one of these two have to be nonlinear to have to use an EKF. Otherwise, obviously, a Kalman filter can be used. We assume that the initial state error and the 2 noise sequences are mutually independent, and the discrete time recursive state estimation filter can be obtained using a series expansion of either first order or up to second order of the nonlinear dynamic and measurement equations. and these two expansions yield either the standard of first order EKF or the second order EKF. The first order EKF requires evaluation of the Jacobians of the nonlinear functions from the dynamics and or the measurement equations, while the second order EKF would require also evaluation of the corresponding Hessians. In my experience, the second order EKF is very rarely going to solve a problem that the first order cannot solve. So while it is of interest from a theoretical point of view, practically the first order EKF is pretty much the only one that is in practical use if necessary. The first order EKF now consists of the following steps. State prediction, so this is again within one cycle you predict from the previous estimate one step ahead, and you use the nonlinear function, the dynamic equation of the previous state estimate. So that function of the previous state estimate based on the dynamic equation gives you the predicted state for the next sampling time. There's a covariance of the state prediction that we need. The covariance propagation equation is the same as in the linear case, except that the Jacobian of the dynamic equation, which has to be evaluated at the previous state estimate, will play the role of the transition matrix from the linear Kalman filter. The measurement prediction is done using the nonlinear function of the predicted state. So that is given by the measurement equation. And the covariance of the predicted measurement, which is really the same as the innovation covariance, would use the same equation as in the linear case, again with the exception that the Jacobian of the measurement equation, which has to be evaluated at the predicted state, will play the role of the measurement matrix. So equations are the same, but we need Jacobians, and they have to be evaluated at some point, and we use the latest available information. The filter gain calculation and the state update and the covariance of the updated state are all identical to the linear case for the first order EKF. We know that there is a coupling now between the state estimation and covariance calculations. The covariances are not available offline, they are not state independent or measurement independent, because we use the latest state estimates in the linearization or in the Jacobian evaluations of the nonlinear dynamic and or measurement equations. So we have obviously a different more complicated setup, and this is the motivation for what was indicated as an absolute need to do extensive Monte Carlo runs on nonlinear filters to verify that they work well.